This is section 10.2, plane curves and parametric equations. This topic 2 is a review of material that you learned in pre-calculus. Let's start with this example. Consider the path followed by an object that is propelled into the air at an angle of 45 degrees. The rectangular equation that they have for this is y equals the opposite of x squared over 72 plus x, which is basically describing the parabolic path in terms of x and y that this follows. Okay, and of course only part of that curve is germane to our problem. So in order to make it just this part of the curve, we have to say something like, but y can only be greater than or equal to 0, or find the domain from x equals something to x equals something, and say that we restrict it to that part, because that model otherwise, of course, would continue down into the ground, but which of course doesn't really happen. And it would be coming up out of the ground and be at the ground level at time 0. But what's better for this is to describe x and y both in terms of a third variable called the parameter. And typically the parameter is going to be the letter t, and sometimes theta. When it's an angle that's changing, we'll use theta, but most of the time it's t, and t almost always represents time. And so the parametric equations that describe this say that the x-coordinate is dependent on t by this equation. X is equal to 24 square roots of 2 times t. And y is controlled by this equation. Y equals negative 16 t squared plus 24 square roots of 2 t. So both x and y are dependent on the parameter t. And so what that gives us is the chance to not only say that's the path that thing followed, but we can then add to that information about it was right here at time 0. So if you put 0 into those two equations, you'll get the coordinate 0, 0. X is 0 and y is 0 when t is 0. And at time 1, it's right here. And you could get the coordinates of that point by substituting in 1 for x. Substituting 1 in for t in the x equation gives you 24 square roots of 2. And y, if you put 1 in for each t, you'll get 24 square roots of 2 minus 16, etc. And so that's an important thing, is that we can say when something is at a particular location, and we can also describe this as the direction of movement along our curve. Whatever this object is following that path. And so having parametric equations adds something to the model y equals opposite of x squared over 72 plus x, because not only do we know where we are at any particular time, we also know the path of movement. So that's a pretty nice use of parametric equations. So that takes us to the definition of what a plane curve is. A plane curve is if you have f and g as continuous functions of t, or theta, on an interval I, then the equations x equals f of t and y equals g of t remember those are continuous functions, okay, form parametric equations, and t is called the parameter. Okay, so this is a set of parametric equations. The set of points xy obtained as t varies over the interval I is the graph of the parametric equations. Taken together, the parametric equations and the graph are a plane curve, and we can denote that plane curve with the letter C. So when you're sketching a curve represented by a set of parametric equations, we can simply just plot points on the xy plane. And we can find each of those points by finding their values, like I did before, by substituting in different values for t. You should probably do that in sequential order, starting with the lowest time to the highest time, if t stands for time, so that you can also determine the direction of movement, also called the orientation of the curve. All right, so let's do an example. We're going to sketch the curve described by the parametric equations x equals t squared minus 4 and y equals t divided by 2. All right. And furthermore, we're given a domain statement about t. We're going to have t start at -2 and go to 3. You may be curious about how, if t stands for time, how you can have negative time. Well, that actually does make sense if you think about it. Time is sort of an arbitrary construct that we've invented, and I could say, well, when I snap my fingers, that was at time 0. And so anything that happened before I snapped my fingers would be considered time before that event, and we would represent time before an event with negative time values. So that's not a strange concept. So since we're going from -2 to 3, I could put in all kinds of decimal and radical values if I wanted to, but I find it easier, and you probably will too, to substitute in integer values for t for substitution purposes and graph those points and see if that's enough information to figure out what kind of curve we'll have. If it's not enough information, you can always fill in with more values of t between -2 and 3, like maybe -1.5 and -0.5 and 0.5 and 1.5 and 2.5 if you needed that information. So anyway, let's do x first. When t is -2, -2 squared is 4, 4 minus 4 is 0. Substituting -1, I'll get -3. 0, I'll get -4. 1, I'll get -3. 2, I'll get 0. And 3, I'll get 5. Okay, now y. When t is -2, I'll get -1. -1, I'll get -1/2. 0, I'll get 0. 1/2. 1 and 3/2. Okay, so let's plot this curve in the xy plane. Notice there's no t-axis here. We're still graphing in the xy plane. That will not have changed. Looking at the x values, I know that the highest value I'm going to be graphing is 5, and the lowest is -4. So I'm going to make sure that I can get to all those x values. And the y values seem like the lowest is -1. So that's 1 and 2, and that's probably high enough. Okay, so 0, -1 is this point right here. And you can designate that it's at time -2 if you want by labeling it. Then -3, -1/2 when t is -1. -4, 0 when t is 0. negative 3, positive 1/2 when t is 1. 0, 1 when t is 2, and 5 3/2 when t is 3. Now notice those are all of the lowest and highest values. We could graph more in between, but we should not graph anything else besides what we've already plotted. So when we go to plot this, we're going this way along the curve and stopping right there. Notice I did not put arrowheads on the end of these domain statement because it's not supposed to keep going. So that's the entire graph, and now that I've drawn it, if you looked away when I was drawing it, can you tell which way I went? Well, the labeled t values help, but I'm going to ask that you always give me the orientation of the curve by putting several arrowheads along the orientation so that it's very clear which way you're moving along that curve. You may be curious, well, what is the equation of this, not parametrically, but using regular x and y? Well, to find what we call the rectangular equation, that is the equation in terms of just x and y, is of interest because we want to know how they're related to each other without having the intermediate, or not intermediate, but the other variable, the parameter in there. So the rectangular equation is often of interest to us. And to produce it, we're going to do something called eliminating the parameter. So to eliminate the parameter, one of the things you can do, I need to be able to see that equation up there, is in this particular situation, this is particularly good for the technique I'm about to show, is pick one of the equations to solve for your parameter t. Always pick the easiest one, which I think is the one that has y equals t over 2, and solve that equation for t. So you would multiply both sides by 2 to get what t is equal to. Then substitute into the other equation for each t with what t is equal to. In this case, 2y is the same thing as t. So if I were to simplify that, I would get x equals 4y squared minus 4, which totally makes sense, that it's a parabola that opens sideways because it's y that's squared, and it's to the right because 4 is a positive coefficient of y squared, and then that minus 4 just shifts 4 to the left. So this graph totally makes sense to me. The only restriction we would need to make to get only that part of the graph, it would be insufficient to say x is between -4 and 5, because that would imply that the bottom half of that graph should have had points down below the axis until x is 5, which would not be sufficient. We need to make sure that we only get those points. The only way we could do that is to say, we'll use y values between -1 and 3/2 only. So y would be on the interval -1 to 3/2. Or another way to say that would be to use inequalities, which makes it clearer that that pertains to y. And with that restriction, we would get that graph. Now the only thing we couldn't get is the orientation, except for by doing some kind of description, like it starts at a certain point, moves left and up, goes to a certain point to the left, and then moves up and to the right, or something like that. A verbal description would be the only way you could get the orientation clear using the rectangular equation. So let's take a look at another example. Let's look at example 2. We've got x equals 1 over the square root of t plus 1, and y is equal to t over t plus 1. And they tell us we can only use t greater than -1. Part of that should be really clear. If t were -1, we'd be dividing by 0 to get x, and if t were less than -1, we'd be taking the square root of a negative number and not getting a real answer. So that domain restriction, t greater than -1, is actually required by the expression for x and y themselves. Okay, so we're supposed to sketch this curve by eliminating the parameter and adjusting the domain. All right. In other words, we're not supposed to make a table of values. They want us to eliminate the parameter. Before I do that, I want to say that sometimes graphing with it in parametric form is easier. Sometimes graphing with it in rectangular form is easier. And so we're going to do a little bit of both, and then we'll talk about perhaps how you know what that should be. So, which one of these two equations do you think we should solve for t? Well, the second one with y in it has two separate t, and you can solve for t, but it's a little bit more challenging. The other one has only one t in it, so I think that might be easier. So to get t by itself, one thing I could do is square both sides to get rid of that radical. Please be aware that when you square both sides of an equation, you might be creating extraneous solutions. For example, if you have the equation x equals 5 and you square both sides, now all of a sudden not only is 5 a good answer, but so is -5. -5 doesn't make the original equation true. So you need to be aware of that. And one thing that you should notice perhaps is that radical in the denominator only has positive results. And +1 divided by a positive number means that x will definitely only give you positive results. So we might make note of anything like that that we see and notice. Radicals only give positive answers unless there's a negative in front of the radical, of course. Okay, so at any rate, so to solve for t, we could multiply both sides by t plus 1 and divide both sides by x squared. Then to solve for t in its final form, that would be 1 over x squared minus 1. Well, I guess it doesn't have to be the final form. You could actually get a common denominator and subtract those two. In fact, let's go ahead and do that. So this would be 1 over x squared minus x squared over x squared, which would be 1 minus x squared all over the common denominator x squared. Okay, now that we've solved for t, let's substitute into the y equation with that value of t. So y will be 1 minus x squared over x squared divided by 1 minus x squared over x squared plus 1. So because this this equation, or I'm sorry, this expression on the right has, it's a complex fraction. It has fractions within a fraction. I'm going to find the common denominator for all the little fractions, which is x squared, and multiply the big fraction by 1 in the form of that common denominator, x squared, over itself. The result will be that I'll not have any of those little fractions left. So when I do that, I'll get in the numerator 1 minus x squared, because of course that x squared cancels. And in the denominator, I'll get 1 minus x squared plus 1 times x squared is x squared. And that simplifies to be 1 minus x squared over 1, which is 1 minus x squared. Now my hope is that y equals 1 minus x squared is something that you are able to graph. And I'm going to graph the whole thing kind of in a naive fashion. And then we're going to talk about what part of it I might have messed up on by not thinking about the original restrictions on t and the one we discovered about x. So 1 minus x squared is a parabola. Because of the negative, it opens downward. And if you add 1, that shifts it up 1. So the negative reflects it over the x-axis, and then we shift up 1, and we get this parabola. Okay, this is the rectangular equation, unaltered, because I haven't yet thought about the ramifications of t being greater than -1 for this graph and x being greater than 0. So whatever t is, I know that x can only be positive from what we said earlier. So what that means is that the actual graph we're going to keep, we can't let x be 0. So we'll have an open circle here. And x can only be positive. So the part of the graph we're actually going to use is what I'm graphing right now in pink. The original blue one, light blue, is not going to be used in its entirety. We're only keeping the part of it where x is greater than 0. So that restriction right there had a huge impact on the graph that we got. Now, oh, and I did something wrong. Let me back up if I can. Let's see if it'll let me do that. Sometimes it's contrary that way. Okay. All right. So I guess I'm sort of happy. I said, you know, this had the big impact. And we have an open circle here, and we're graphing only to the right. Now, I didn't want to put an arrowhead because that would imply a direction of movement. The rectangular equation has that there, but this doesn't. So we don't know which way it's going. But it follows that light blue path, but we don't know if it's going down and right or up and left. And so to determine that, you should probably pick a t value greater than -1, of course, and calculate either x or y, because I think either one by itself is sufficient. So let's pick when t is greater than -1, let's pick 0, and then pick a time after that, 1, and let's see where that takes us. So when t is 0, 0 plus 1 is 1, the square root of 1 is 1, so x will be 1. So at time 0, we're at x equals 1, which is this point right here. Oops. Oh, I guess I can make that work. That's where we are at t equals 0. It's right there at that point. Okay, and at time 1, 1 plus 1 is 2. 1 over the square root of 2, aka square root of 2 over 2, is about 0.707. which is, let's say, right here at time 1. And so as time is going on, it's moving that way. It's moving up towards that open circle. But you didn't think it was going to go that way, did you? It's kind of interesting. Okay. So let's go to example 3. It says, make a table of values and plot the graph of the function defined parametrically as x as a function of theta is 4 cosine theta minus 3, and y as a function of theta is 4 sine theta plus 2. Make sure your graph indicates the direction of movement. All right, so we're going to calculate for various theta values, both x and y. So I'm going to do x first. Some good numbers I might try for theta would be numbers like 0, pi over 4, pi over 2, pi, 3 pi over 2. I'm trying to make these fairly easy to calculate. We can always fill in more, 2 pi, in between if we need to. But I'd like to just see what's going on with these values. So 4 cosine of 0 is 4 times 1 minus 3 is 1. Cosine of pi over 4 is square root of 2 over 2. 4 times that is 2 square root of 2 minus 3. Probably need a decimal for that in a second. Pi over 2 cosine of pi over 2 is 0. 0 minus 3 is negative 3. Cosine of pi is negative 1. Negative 4 minus 3 is negative 7. 3 pi over 2, I get negative 3. And 2 pi, I get 1. Okay, now let's do y values. Sine of 0 is 0. 4 times 0 plus 2 is 2. Sine of pi over 4 is square root of 2 over 2 times 4 is 2 square roots of 2 plus 2. Sine of pi over 2 is 1, so that's going to be 6. Sine of pi is 0, so that'll be 2. Sine of 3 pi over 2 is negative 1, so that will be negative 2. And sine of 2 pi is 0, so that'll be 2. Okay, so let's see. So our x's go all the way out to negative 7. And I'll need to know what that 2 square roots of 2 minus 3 is. So let me type that in my calculator. It's about negative 0.17 something. Okay, now that I know what that is, that's about negative 0.2. I'll call it. And while I'm here, I might as well do 2 square roots of 2 plus 2. It's about 4.8. Okay. Now my y's, oh, and I will use x as positive 1, so I do need that on there. I'll put a 2 there as well. Okay, the y's, I'm going to have to go down to negative 2 and up to 6. Okay, so let's just start plotting points. 1, 2 is the first point. I almost said buckle my shoe. You can tell I have grandchildren, can't you? See the next point, and that's at theta equals 0. I'm probably not going to label all of these, but at least some of them. Let's see, the next point is at negative 0.2, 4.8. 1, 2, 3, 4.8. So it's about right there, give or take. The next point is at negative 3, 6, which is right there, and that's at theta equals pi over 2. Negative 7, 2, about right there. That's where we are at theta equals pi. Negative 3, negative 2, and theta is 3 pi over 2. And 2 pi, we're back to 1, 2. So if you need to, go and find more points and plot them. But I'm going to go ahead, because I know what this is supposed to be, and I'm going to draw a curve that passes through those points nicely. Anybody have a guess as to what that curve is? Well, we'll confirm your guesses here in a minute. So hold on tight. Now, in the order in which we increasing theta values gave us points in a certain order, and so the orientation of this curve is the direction we're moving along this curve as theta increases. Okay, that's the orientation. The next part of this problem is they ask us to eliminate the parameter. So let's do that. I'm going to start with x equals 4 cosine of theta minus 3, and y equals 4 sine of theta plus 2. Now, I will tell you this is different. Whenever trig functions are in your parametric equations, you will not be solving one of them for the parameter. You know, just a little while ago, that's what we did, was we solved that equation, y equals t over 2, for t, and then substituted that into the other equation right here. Right here. That's what we were doing. So, that's usually what you're going to do. The big exception is if there are trig functions in your parametric equations, that is not the way I want you to go. What I want you to do instead is think of an identity that relates the two trig functions to each other. So how are sine of theta and cosine of theta related to each other? You do not want to introduce a third trig function into this. We want an identity that has only sine of theta and cosine of theta in it. Well, I'm hoping you're thinking of the Pythagorean identity, cosine squared theta plus sine squared theta equals 1, because that's an identity that relates sine of theta to cosine of theta. So instead of solving for theta, what we're going to do is solve each of these equations for the trig function. So I'm going to add 3 to both sides, and then divide by 4 to solve for cosine of theta. Likewise, when I solve for sine of theta over here, I'll do that by subtracting 2 from both sides, and then dividing both sides by 4. So into this trig identity that you wrote down that relates cosine theta to sine theta, substitute for cosine of theta with what it solved to be equal to. So x plus 3 over 4 squared plus, now substitute for sine of theta with what it equals, y minus 2 squared, y minus 2 over 4 all squared, excuse me for saying the square too soon, equals 1. And if you do that squaring, you'll get x plus 3 squared over 16 plus y minus 2 squared over 16 equals 1. And that looks like it's the equation of an ellipse, but this is a special ellipse. The x radius and y radius are both 4. And so since this is a circle, it's a special one where the x radius and y radius are the same. You need to write it in the standard form for the equation of a circle, which means that you're going to need to multiply both sides of this equation by 16, because x plus something squared has to be all by itself, plus y minus something squared has to be by itself, equal to the square of the radius, 16. So this equation says we should have gotten a circle whose center should be at -3, 2, and whose radius should be the square root of 16, should be 4. So let's look at our graph and see if that's true. If we plot the point -3, 2 as the center, and then go right 4, we'll get to that point. Yep. Up 4, we'll get to that point. Indeed. Left 4, down 4. Yep. This is a circle centered at -3, 2 with a radius of 4. So that is correct. Okay, so let's move on to example 4. The directions say to eliminate the parameter to find an equation in standard form for each relation. Notice it does not say that we have to graph. So we might graph just for fun, but it doesn't require graphing. Okay, so x equals t squared plus 2t, and y is equal to t squared minus 2t. Okay, this one does not involve trig functions, so we're not doing that identity approach. What we're going to do instead is the first approach, which is to eliminate a parameter. We have to solve one of the equations for t and substitute into the other equation. These two look so much alike that it doesn't really matter which one of those we solve for t. So I'm going to solve x equals t squared plus 2t for t. Now the fact that I have t in there twice and it's quadratic means that I need to make a single t out of that. And the best way to do that when I have a quadratic and a linear term is to complete the square. So half of the coefficient of t squared is 1, so half of t's coefficient, half of 2 is 1, 1 squared is 1. So that means I'm going to add 1 to the right side to complete the square. If I add 1 to the right side, I have to add 1 to the left side as well. And so x plus 1 will equal t plus 1 quantity squared. Okay, so then we're going to take the square root of both sides. Don't forget we should put in a plus or minus when we take the square root of both sides. And then to solve for t, subtract 1 from both sides. Then, now this might argue for the fact that maybe graphing this with the parametric equations as given would be a lot easier then eliminating the parameter, and I think this is a good argument for that. But nevertheless, we're going to do what we were told. So by substitution, y will equal -1 plus or minus the square root of x plus 1 quantity squared minus 2 times t, which is again -1 plus or minus the square root of x plus 1. All right. So squaring that binomial, I will get +1, then 2 times the first thing, -2, times, I'm going to do the top, times the positive radical will be a -2 times that radical, plus the square of that radical, which is x plus 1. And the other way of doing it would be -2 times -1 times the negative radical, which would be plus. So in the top version, it ends up being subtraction of that second term. The bottom version, it ends up being addition. And it's important that you keep the order in which you're doing that. You'll see that back here as well. Distributing the -2 times -1 is +2. -2 times the positive radical is a -2 times the radical on top. And then -2 times the negative radical on the bottom gives us a plus. You may have never seen this before, but if something is plus or minus, and the order in which you do it is important, like here it is, that changes the plus or minus into a minus or plus. And I'm thinking maybe that's something you haven't seen before, which means this is kind of cool. You're getting to see new stuff. Yay. Okay, so let's see. I'm looking for like terms. So I've got a constant of 1, a constant of 1, and a constant of 2. 1 plus 1 plus 2 is 4. Okay, then I'm looking for radicals. I have this radical and this radical. If I'm using the top, it's -2 times the radical plus -2 times the radical, which would be -4 of the radical. Or if I'm using the bottom part, it would be +2 of the radical plus 2 of the radical, which would be +4 of the radical. Do you see if you got one of those upside down and you were doing negative for the top and accidentally plus for the top, those would have canceled out to be 0, which is not true. So you got to be really careful about jumping to poor conclusions like that. And then the only other thing I haven't looked at yet is this x. So I'm going to put that x back here like that. Okay, well, I'm glad they didn't ask us to graph this, because graphing that wouldn't be any easier in this form than in the other form, but this is what you would get. So what I'd like for you to do is, in your calculator, you're going to graph two things for this. In y1, type 4 minus 4 times that radical plus x. Don't forget to get out of the radical. In fact, you might want to write it in this order instead, just to make sure you don't have that issue. Let's do x plus 4 minus 4 square roots of x plus 1. Type that in y1. And then in y2, type x plus 4 plus 4 square roots of x plus 1. And what you should see, although probably not perfectly drawn, but not too bad, I guess, is something that looks like this. Something like this. A parabola that doesn't open to the right nor does it open up. It's kind of somewhere in between. So that's kind of an interesting answer. Oh, I shouldn't have drawn those arrowheads. Because, well, we would have to do the orientation of the curve. Let me just take those off and say I don't know the orientation of the curve without doing a little bit more investigation. Would you like to figure that out? Okay, let's do it. If I say let t be something easy, like 0, and then 1, what would x be, and what would y be? Okay, so I want to find both of them this time. Okay, when t is 0, x will be 0. When t is 0, y will be 0. So we're right here at the origin at t equals 0. When t is 1, 1 squared plus 2 times 1 is 3. When t is 1, 1 squared minus 2 is -1. So that means we're out here at 3, -1, somewhere about like right there at time 1. So that means our direction of movement is that direction. As t increases, which way is it moving? Okay, so that's kind of cool. Let's move on to B. All right, so problem B. And again, on that last example, the graph wasn't really part of it. We were just supposed to arrive at this rectangular equation at the bottom in the middle there, which we did very well. All right, so B, x is equal to 6 sine of 2 theta. Okay, so this is a trigonometric one. So this is, remember, we're not solving for theta, we're solving for the trig functions. And y equals 4 cosine of 2 theta. So that means that x over 6 is equal to this trig function sine of 2 theta. And y over 4 is equal to cosine of 2 theta. Now, is there an identity that relates sine of 2 theta to cosine of 2 theta? Well, yeah, there is. It's the Pythagorean identity. It doesn't matter what the angle is, whether it's theta or 2 theta or 17 degrees or whatever. Sine squared of that angle plus cosine squared of that angle, as long as they match, angles, that is, they match, you should get 1. So that means that we're going to, by substitution, get x squared over 36 plus y squared over 16 equals 1, which, of course, is an ellipse. Its center is at 0, 0. The x radius is 6. The y radius is 4. So when we graph this, in the xy plane, let me put some marks on here. On the axes, so that we have a chance to graph it all. Okay, so the center is at 0, 0. Our x radius is 6, so we're going to go from the center right 6 and left 6. And the y radius is 4, so we'll go from the center up 4 and down 4. And then do our best to draw an ellipse that goes through those. Now I started at one place and I'm going a certain way around. That doesn't mean that's what it's supposed to be doing. It's just me trying to get the graph on paper. So we'll get this graph, and now let's worry about orientation. Well, especially with the 2 theta in there, I'm a little bit nervous about picking thetas that are not extremely close to each other. So I'm going to pick some that are really close, like 0 and pi over 8. Because it's possible if I pick like 0 and pi, let's just say that 0 and pi gave me points here for 0 and here for pi. Do you know which way I went around? No, I have no idea. But if I said 0 is here, I'm just making this up, and pi over 8 was right here, then I'd know the orientation is that way around, or whatever happens in this problem. So you got to be careful that these two have to be fairly close so you can figure out which direction you're moving. So sine of, doing x, sine of 0 is 0, 6 times 0 is 0, 2 times pi over 8 is pi over 4, sine of pi over 4 is square root of 2 over 2, 6 times square root of 2 over 2 is 3 square root of 2. Okay, now for y, cosine of 0 is 1 times 4 is 4. So at 0, we're actually starting up here at theta equals 0. We're at the point 0, 4. Okay, so I started at the wrong place totally, but that's okay. Okay, then let's see. When y is pi over 8, 2 times pi over 8 is pi over 4. Cosine pi over 4 is square root of 2 over 2 times 4 is 2 square roots of 2. So 3 square roots of 2 is about 4.2, and 2 square roots of 2 is about 2.8. So 1, 2, 3, 4.2, 2.8, we're about right there. And it don't have to be super exact, you just have to be in the ballpark. So to me, this is pretty clear that this is moving clockwise around the ellipse. Okay, and again, I did the graph sort of as extra. The answer we were looking for was that equation, x squared over 36 plus y squared over 16 equals 1. But doing the graphing helps you kind of get a fuller picture of everything that you might be asked to look at for a given problem. Okay, so let's look at C. Okay, C is x equals 4 tangent of theta minus 2, and y is equal to 3 secant of theta plus 1. So what I'd like for you to do is solve both of these equations for the trig function. Remember, when there's trig functions in there, you solve for the trig function. Then see if you can think of an identity that relates tangent of theta to secant of theta, and substitute into that to get your rectangular equation. So I would like for you to pause and do that, and then come back when you're done. Okay, hopefully you got this one right. We shall see as we go through it. All right, so when you solve for tangent of theta, I hope you got x plus 2 all divided by 4 is what tangent of theta is. And I hope you got that y minus 1 all divided by 3 is what secant of theta is. Then I hope that you came up with the identity tangent squared theta. It's one of the Pythagorean identities. Tangent squared theta plus 1 equals secant squared theta. So by substitution, that's going to be x plus 2 over 4 quantity squared plus 1 equals y minus 1 over 3 quantity squared. So usually those fractions involved in these are together equal to 1. So I'm going to leave that 1 alone on the left side and subtract to get y minus 1 squared over 9 minus x plus 2 squared over 16. So that's a hyperbola. It's a chance to review conic sections, by the way, whose center is what? I hope you said -2, 1, and not 1, -2, because the x-coordinate is with x and the y-coordinate is with y. The y-radius is 3. The x-radius is 4. By the way, when we're in class, remind me if you'd like to know how to graph the parametric equations in your calculator from that form. That's another reason this rectangular equation, to solve, you'd have to solve it for y and graph y equals something, which would be very hard for these quadratics to do and get correct. But graphing the parametric equations in your calculator with this is super easy. So in class, remind me to do that with you, because it's a worthy endeavor to think about it. Okay, so just give myself some marks on the axes. Okay, so the center is at -2, 1. The y-radius is 3, so I'm going to go up 1, 2, 3 from the center and down 1, 2, 3. The x-radius is 4. So from the center I'm going to move right 1, 2, 3, 4 and left 1, 2, 3, 4. And then I'm going to draw the box for the hyperbola. Or the ellipse, we draw the ellipse through those 4 points. But we're drawing the box where those 4 points are the midpoints of the sides of the rectangle. Then we draw the diagonals of that box, which end up being the asymptotes for the curve. And it's really hard not to draw the arrows on the curve. On the asymptotes is fine, but on the curve you don't want to draw them, because we're going to have an orientation, and that arrowhead at the end means that that's the orientation, and I know what you mean by the arrowhead at the end is supposed to be keep going. So anyway, now how do we know if this opens up and down or if it opens right and left? Well, recall the determining factor there is, look at the positive fraction. What variable is in that positive fraction? It's y, which means that we're going to go up and down from the center to get to the vertices. So the red points are the vertices. And, oh, see, I did it. Hold on. I drew the arrowhead, and I wasn't supposed to. Okay. Told you I'd forget. It's hard to remember. I'm so used to doing it otherwise. Ah, that was not very clean. Try again. Okay. Now, I want to show you this on the calculator and how you get the orientation on the calculator. So I'm just going to tell you that it ends up being this way, like that, and then this way. And I want to show you this on the calculator. It's really cool, and it's a little bit more satisfying than plotting a whole bunch of points and figuring out what the orientation is. Your technology can do that. Okay, yeah, that's a good stopping point. So I'm going to stop this one and go to another recording for the continuation.